Good morning. Today I will present the seminar of the week entitled How Quantum Simulations Can Help in Sustainable Energy Research. The global economy and our quality of life is heavily dependent on energy demand. The per capita demand for energy has been increasing exponentially over the years, and it is extremely important that we think about ways to generate energy in a clean, sustainable, and safe way. Well, nowadays, the generation and consumption of energy that lives reduce, such as the burn of fossil fuels, for example, is the main cause of global warming. So in the previous seminar, I talk about techniques for simulating the properties of a system using first principles, in particular DFT. When we study sustainable energy research, we often want to understand the behavior of electrons, their excitations, transport, and interactions. So therefore, simulations that employ quantum mechanics can play an important role of solving several problems related to sustainable energy. So, simulation methods provide access to a range of system types and accuracy. In this figure, we see some examples of sustainable energy research and different methods to address these problems. As already mentioned in the previous seminar, DFT methods use the electron density as the main variable, justified by the Hohenberg-Kohn theorems. Using a set of equations called the Kohn equations, we can correctly obtain the kinetic energy of electrons. Orbital free density functional theory uses the kinetic energy density functional to approximate the kinetics of electrons. So mainly use it to treat semiconductors and transition metal systems. Um, Beneficial aspects of different methods can be exploited simultaneously in one simulation by using embedding schemes, like embedding correlated wave functionals method, for example. His package of physical models and computational algorithms is validated by simulating experimentally known and relevant physics properties. From now, I will show some quantum solutions using computational simulations of some relevant works. I will mainly deal with two topics that are nuclear fission reactors and solar energy conversion, and I will only present the main conclusions of these works, and I will not go into details of the results, but we can discuss at the end of the seminar. Well, nuclear fission reactors basically simulated our sun, in which deuterium and tritium nuclei are combined at ultra high temperatures for from high energy neutrons and helium nuclei. Heat transferred from these high energy particles can be used to generate power. So optimizing materials is an area which material science can contribute. Reactor walls must withstanding not only relatively high temperatures, but also continuous bombardment by high energy neutrons. These high energy particles may transfer charge and energy to atoms, lining the reactor walls, first walls, atoms, form chemical bonds within and produce defects, embrittlement, and ultimately material deterioration. A potential solution for this is to cover the vulnerable solid walls with liquid metal films, which are immune to Suki degradation. One promising metal to this is lithium. Its behavior under deuterium ion bombardment has been simulated at multiple length scales to determine the conditions on which a flowing thin film will remain stable. So, DFT simulations reveal correlations between lithium and deuterium diffusitives indicate of chemical bonding between the two. At temperatures below the melting point of a liquid lithium deuteride, crystallites of a lithium deuteride nucleate in the liquid, causing a step reduction in diffusitive of both lithium and deuterium. DFT and molecular dynamics is a powerful tool to simulate interactions between liquid metal switch walls, and we can to predict relevant macroscopic properties of a liquid lithium, such as melting point, structure factor, viscosity, diffusivity, and surface tension. The nucleation sequesters deuterium in liquid lithium, explaining the observed anormally low liquid, lithium sputtering. This property could stabilize the reactor feed walls beyond the capability of pure liquid lithium, which otherwise may evaporate from metal substrates at these temperatures. So here we can see densities of pure liquid lithium, and pure liquid lithium is the solid circles, and the liquid lithium samples with 4 different deuterium concentrations. So we can observe that the density grow. Um, these quantum solutions suggest a design principle. High deuterium concentrations in liquid lithium nucleate solid liquid deuteride, sorry, which could improve the thermal robustness of re, robustness of the fusion reactor first walls. Well, solar energy conversion transforms sunlight into electro, thermal, or chemical energy. First row transition metal oxides and sulfide materials have received considerable attention for this purpose, that are inexpensive, catalytic to achieve, and appear in many devices such as photovoltaics, dye-sensitized solar cells, packs, and concentrated solar thermochemical reactors. So quantum
Like
simulations,
2 minutes.
okay, can explore the doping and alloying of such materials to optimize key properties such as band gaps, band edge positions, charge carriers, and ion mobilities. For example, nickel oxides have a large band gap that results in only meager light absorption. DFT calculations indicate that allowing nickel oxide with lithium oxide will lower the band gaps by as much as 1 point electron volts without affecting other favor properties. So alloying instead with manganese oxide or zinc oxides transform nickel oxides from a 2D into a 3D conductor by reducing interplane role transfers barriers, make it an intriguing candidate for a transparent conduction oxide in photovoltaics. Alloying nickel oxide with manganese oxide and zinc oxides retains the the large band gap of nickel oxides and hence its optical transparency while improving its conductivity. Because nickel, manganese, and zinc are all inexpensive elements, this material could replace, for example, conventional transparent conduction oxides in photovoltaics that contain rare and therefore expensive element indium. Um, a new mechanism for solar energy conversion makes use of plasmons in metal nanoparticles. Bulk gold is mostly inert. Also, gold nanoparticles do catalysis reactions at elevated temperatures. Alternatively, at room temperature, visible light illumination of coinage and aluminum metal nanoparticles. Okay, I'm finishing. Excites collective electrons oscillations, né? That is plasmons. These plasmons can decay to produce hot electron roll pairs that catalyze several chemical reactions. DFT has trouble treating excitations and charge transfers. By contrast, embedded correlative functionals theory contains the right physics to do so and has identified two distinct mechanisms for hydrogen dissociation catalysis. Charge transfer excited states with reduced barriers facilitated hydrogen dissociation on gold, whereas resonant energy transfers enables to semi-catalysis on aluminum. So, quantum simulations, such as DFT, can bring us many insights in sustainable energy research. Here I have shown some examples, but these methods are still useful in various types of research, such as water splitting and energy storage as batteries. The usefulness of quantum simulations will only increase as they further mature and become more reliable and easier to use. And that's it. Thank you.